Everybody. This is the lecture number, I guess, 15, and this is the second practice series in the series of the fluid mechanics for GATE 2026. So the today, the lecture that we are going to discuss here is the practice program. I've taken 5 practice program on the topic of the viscosity of the first chapter of the fluid mechanics. Okay, so the first question, in the whole practice programs, this is the question number 7, but in the subtopic of viscosity, this is the first question. Okay, the first question that we are going to discuss here is, it is as a fluid flowing over a flat solid surface. This is the flat solid surface, right? This one, and a fluid is flowing over there with a parabolic velocity distribution. Okay, the vertex of the parabolic distribution is situated 10 centimeter away from the solid surface. Okay, that means this is the solid surface. Okay, and 10 centimeter above the solid surface, the vertex of the parabola is situated. The maximum of the velocity, V max is situated at 10 centimeter from the solid surface. Okay, where the fluid velocity is 1.5 meter per second. That means the maximum velocity that we are getting there is 1.5 meter per second. The shear stress at the 0.5 centimeter from the solid surface is determined by 30 Newton per meter square. It is tau at 5 centimeter. Okay, it is given. The 5 centimeter is from this solid surface. That's why I have written here by. Okay, that means this is by equal to 0. This line. Okay, and the fluid follows Newton law of viscosity. Okay, that means we can use that one. What to say? Tau equal to mu du by dy. Okay, so this means that the fluid will follow Newton's law of viscosity. So we can use that equation for finding the shear force or the shear stress. So the first thing that the question is asking here is the viscosity of the fluid is. Okay, so we have to find the viscosity. Okay, mu, the coefficient of viscosity, it is asked here. So from the given information in the questions, I have drawn the picture here. So the general equation of the parabola I have written here is u by equal to a by a square plus b by plus c. Okay, this is the general equation, right? Parabolic equation that we have studied in our school days, right? Now the first condition that I am applying here is this one. The first condition is at y equal to 0, no slip condition. That means the velocity of the fluid is 0 here, right? No slip condition. I have discussed it here in the previous chapter. Okay, I have discussed everything in the detail. So please watch the lectures if you are not able to understand the program. Okay, so no slip condition. That means the velocity will be 0 at the near the wall. Near the wall, just at the ball, that is at y equal to 0. So we can put it at y equal to 0, and we will get only the c value, and that will be equal to 0. That one we will get that c equal to 0. Okay, now velocity profile is after eliminating c, we got here at that c equal to 0. So after eliminating that, we will get u by equal to a by square plus b by. Okay, now we know that at y equal to 10 centimeter, that is 0.1 meter, the velocity that we have provided is 1.5 meter per second. Okay, in the question it was given, so we will use just put the values 0.1 at the position of y, and we will equate it with the 1.5. Okay, so we will get that a plus 10b plus equal to 150, right? I have just multiplied both sides with 100. Okay, here 100 and here 100. Okay, so this will become 1, this will become 10, this will become 150. Now we can also know that we also know that the velocity at this point is maximum, right? This is the property of the parabolic profile, right? And the vertex of the parabolic profile is maximum point. Okay, that means we can say that derivative of that velocity at that point should be equal to 0. That's why I have written du by dy at 0.1 is equal to 0, right? So I have differentiated velocity with respect to by. So after differentiating, what we will get is 2a by plus b, right? By square will get us 2 by, and by is 1. So I put in a b here only. Okay, so and when I put 0.1 here, so it will become 0.2a, b will remain b, and a, so the a will become equal to minus 5b. Now we can equate both the equation. We will get as minus 5b plus 10b will equal to plus 5b, right? Equal to 150. So what will become? It will become b equal to 30, and a we can equate it from there. That is 1 minus 150. Now we got the velocity profile, right? The value of a and b we got here. So we can now write it u by equal to minus 150 by squared plus 30 by. So the shear stress, as we know that the fluid follows Newton's law of viscosity, right? It was mentioned in the question. So we can use the shear stress formula, tau equal to mu du by dy at y equal to 0.5. Okay, because it was given at 5 centimeters, so we can write it as 0.5 meter. Okay, so I've written here 0.05. So now the value is given 30, so I put it here 30. Mu is unknown, we have to find it that, and the du by dy I demonstrated it here, and what we will get is 2ay plus b, right? Okay, and 2a by means if you put y equal to 0.5 and b is just constant, okay, 30. Okay, so now you will equate and you will get that u equal to 2 newton second per meter square. So the first question is done. That means you have we found the value of coefficient of the viscosity. Okay, and the second question that was asked is shear stress at a solid surface is, okay, that means tau at y equal to 0, right? So we can just apply this formula at y equal to 0. Okay, just simple. And what we did is, if you put, I mean, if you differentiate you will get 2a by plus b. Okay, I'm putting making it again. So y equal to 0 means this term is get vanished, only b will be there, and multiplied by mu. 30 into mu, the value of b is 30, so you will get 30 into 2 is 60 newton second per meter square. Okay, I have used mu value that we have found it in the previous problem, right? Just put the value of 2 here, and 30 into 2 is equal to 60 newton second per meter square. Okay, so I hope the above question is clear to you. Now we are going to discuss another question, the question number 8. So the question number 8 says square thin plate of length 80 centimeter and mass 30 kg. Okay, so this is the square plate, the above one. Okay, and the length of the plate is 80 centimeter and the mass is 30 kg. Slides parallel to a solid plane surface inclined at an angle of 60 degree to the horizontal. Okay, so it's saying that one solid surface is there. I mean, in this case it is this, and in the solid surface is this, and this is the moving plate. Okay, so it is inclined at 60 degree and it was moving moving above the solid surface, and in between a Newtonian fluid was given. Newtonian fluid means, again, it will follow tau equal to mu du by dy. Okay, please be aware of that. All the questions are based on that only. Okay, and the layer of thickness is 2 millimeter is present in between the plate and the plate surface. Okay, that means the thickness is 2 mm. Okay, the fluid thickness is 2 mm here and here as well. Okay, I mentioned here L equal to 2 mm. Okay, had the plane been horizontal, now the question is giving a condition like, if the these plates are in a horizontal plane. I mean, the original question is it was given at angle of 60 degree, but the question is mentioning an arbitrary condition where the plates are not in angle, they are on horizontal plane. So they are mentioning that if a constant force of 192 newton would have been applied, so it will move with a velocity of 3 meter per second. Okay, so these are the condition given. I mean, the arbitrary condition, and the actual condition is 60 degree. Okay, so if the fluid velocity can be assumed to be linear, I mean the fluid velocity supposed to be linear. Okay, then the constant force to be applied parallel to the inclined plane on the plate to make it slide an instant velocity of 6 meter per second. Okay, so one arbitrary condition of the horizontal plane has been given. Now they are asking for a inclined plane, and they are asking a force that is required for the plate to move at a velocity of 6 meter per second. Okay, so now first we will find it out that coefficient of viscosity, right? The coefficient of the viscosity is not known to us. So we will find from this case the horizontal case, because in this case both the force and the velocity is given, but in this case only the velocity is given. So using that coefficient of the viscosity we will find out the force. Okay, so now we know that the shear stress, it can be written as, so Newtonian fluid is given, that's why it is written. Okay, and for linear velocity profile we can simply write as du by dy equal to v by l, right? So I've just put it here. V, the value of v is 3 meter per second, and divided by L is 2 millimeter. Okay, so 2 into 10 to the power minus 3. Now F equal to AU V by L, MU V by L. We know that the area is 80 centimeter, length is 80 centimeter, and it is a square plate. So we will just make it here A square, right, or equal to A into A, and A is 0.8. So I put it here 0.8 into 0.8 multiplied by mu, and here 3, and a length is 2 into 10 to the power minus 3. Okay, and the value that is coming is 192. I mean, the value that is mentioned in the question is 192 newton, right? So from there mu is only unknown, and we can find it out, and it will come as 0.2 newton second per meter square. Okay, so we have found the mu value. Now we can find it out force, right? That is applied, we will apply the same formula, 0.2, 0.8, 0.8. We have found the mu, right? So 0.2, 0.8 into 6. I mean the 6 is the required velocity, right? They are asking 6 and divided by length. Length in both cases, in the horizontal and the inclined plane, both are same. The length are same. So I have put here 2 into 10 power minus 3, and that is the force coming is 384 Newton. Okay, so the question doesn't end here. One more trick is there, like in inclined planes, some act of gravity will also act here, right? So I mean along the plate one force will come, right? Since it is an inclined plane, right? In a horizontal plane only the gravitational force is acting is in the downward direction. Okay, that means the net force acting along the plane, along the plate, or the tangential to the plate is zero in the web cases. I mean in the horizontal plane cases. But in this case some force will act, that is w sin 60 degree. So this force is acting I mean prior to applying our forces, right? So we have to minus the this force from total force, right? This force is inbuilt, right? So we have to apply some lesser force than the required I mean the required force, right? So the required force is 384 minus that gravitational force that is acting by its own. So 384 minus mg sin theta, and it's coming as 129.13 Newton. Okay, so I hope this question is also clear to you. Now I am moving to another question. The another question says that in a journal bearing of length 500 millimeter, okay, this length is given, 200 millimeter diameter shaft is rotating at 1000 rpm. Okay, so shaft diameter is 200 and it is rotating at a speed of 1000 rpm. So we can find it out the tangential velocity developed here is I mean ut equal to pi dn by 60, right? So we can find it out as pi, and d here it is given 0.2 and 1000 over 60, and the tangential velocity is coming is 10.472 meter per second. Okay, so and the uniform space between the shaft and the journal bearing is completely filled with an oil. Okay, that is Newtonian fluid. Again we can apply that Celestis formula. So I have written here AP is equal to A into mu into du by dy. Okay, the force required, and the coefficient of viscosity value, I mean mu or alpha, anything you can write, 0.9 Newton second per meter square, and the energy is being dissipated is 15.5 it is here. Okay, what is that? For 15.5 kilojoule per second. Okay, while overcoming the velocity profile, and the velocity profile is linear. Okay, so they are asking what's the should be the I mean the thickness of the fluid. Okay, these are the fluid here. Okay, and this is the bearing ball, this is the shaft, and in between the bearing ball and this shaft one fluid layer is there, and I'm assuming the length of this fluid layer is delta for now. So I've computed force as 0.9 into 0.2 into 0.5 into 10.472 divided by delta. Okay, so I mean for let me explain you. Mu is 0.9. Okay, I've used that value first here, and area is 0.2 into 0.5, right? 0.5 into 0.2. I mean if you take that rectangular part, if you see from the cross sectional view, you will get a rectangular part, and that area is equal to 0.2 into 0.5. Okay, so the energy dissipated can be found out force into velocity, right? The unit of this will be in kilojoule per second. Okay, so the kilojoule I have converted it into joule per second, so it's coming as 15500, and I have computed with force and multiplied by 10.472, that is the tangential velocity. Okay, and now I have found the I mean the fluid length, and that is coming as delta is equal to 2 millimeter. Okay, so I hope this question is also clear to you. Now I'm moving to the next question, and the next question says that two vertical plates are there, I mean two vertical walls are there, and one metal plate is inserted in between this vertical gap, and the vertical gap is containing some fluid. Okay, Newtonian fluid, precisely of viscosity 3 Newton second per meter square. Okay, and the width of that wall is 5 centimeter. I mean the gap is 5 centimeter, and the specific gravity of the fluid is 0.5, and then here the dimension of the metal plate is mentioned, and the weight of the that is metal plate is 15 Newton is mentioned here, and it is asking that how much force required to lift the this plate with a velocity of 0.5 meter per second. Okay, here it is said. Okay, now same thing is mentioned here. That means they are mentioning that the metal plate is having a distance of 2 centimeter from the left plate, right? It is mentioned here. Okay, So they are asking the force required. Okay, so now we will apply the same formula, that is FL equal to A into mu into B by DL. As the linear velocity profile is mentioned here, we can use that P by DL directly. Okay, so area is 1.5 into 1.5 and mu is 3, right? It is given in the question. Yeah. So 3 into velocity they are asking is so it is 0.5 meter per second, 0.5, and DL, I mean the distance from the left hand side. So we are finding out shear force on the left hand side of the plate. Okay, from the left wall. Okay, so it is coming as 168.75 Newton. Now similarly we can find it out from the right wall. Okay, so we will apply the same formula, and the distance we can find it out as a total distance is 5, and the width of this plate is 0.5 meter, sorry 5 centimeter, and this is 2 centimeter. Okay, so the distance from the right plate is 2.5 centimeter. Okay, so I just changed the value of dr. I mean instead of dl, I've just choose dr. Just substituted the value 2.5 into 10 to the power minus 2 meter, and the value I get is 135 Newton. Okay, that means the shear force acting on this, I've drawn here the force body diagram of the plate. Okay, and the left shear force acting here is FL in the downward direction, right shear force is acting here in downward direction. Okay, so left shear force that we have found it out here is 178.75 Newton, and here we have found it as 135 Newton, and weight it is given as 50 Newton. Okay, and we are neglecting FB here for now. Okay, so now the force required to lift the plate will be the sum of all these three, right? All these three are acting in the downward direction. Okay, so we will just add all of them and we will get the required value, right? So the required value is 353.75 Newton. Okay, so this is the required value, and that's all for this question. So again, I hope that you people understood the problem and the solution. Okay, so now I'm moving to the last question for this lecture. Okay, and the last lecture is a solid cylinder is given, this one, the brown one, with a diameter small d, and a larger cylinder cavity is given with the green one, which is having diameter of capital D. Some weight of this solid cylinder will be there for sure, and let's suppose one acceleration is given m, and viscous force will act on the upper direction for sure, because the fluid is filled here between the solid cylinder and the cavity cylinder. The gap between both of them have been filled with the fluid. Okay, and it's given that the clearance between pipe is filled with the Newtonian fluid, and density of the fluid is rho and mu. Okay, now they are saying that for this clearance the terminal velocity of the fluid is determined to be v. Assuming a linear velocity profile, we will have to assume a linear velocity profile, and the terminal velocity is given as v. Okay, now however, if we change the property of the fluid to the density to be double of that, and viscosity to be double of that, so they are asking that now the force required is, for the same force required, the velocity coming as f1. Okay, so now they are saying that what should be the relation between the previous velocity and the final velocity. The force acting is same, the thing that changed here is the property of the fluid. Okay, so now I am written here the next force balancing after balancing on solid cylinder. If we draw the FBD diagram of the solid cylinder and if we balance the force, we will get that F equal to W minus D. Okay, W is there in the downward direction, and viscous force is acting on the upward direction. So in downward direction I have taken positive, and in the upward direction I have taken negative. So I have equated both of them, and that can be equated with the is equal to mass into acceleration from the Newton's second law. Okay, this is easy. Now when solid cylinder attains terminal velocity, then now this solid cylinder will, this will become equal to the solid cylinder. So the net acceleration will get 0. So the force equilibrium will be there. So that means the weight is equal to the drag force, right? So there is no acceleration. Okay, so for linear velocity profile and Newtonian fluid, we will use the same formula, F equal to A into mu into V by air. So area we can find it out as a pi into D into L, right? And this area pi D L. Okay, and mu into V, and the length is there is capital D, capital D minus small d by 2, right? So this is this capital D, this is small d, and this distance is that one. Okay, and weight of the cylinder can be found it out m into z. Mass can be found it out as rho into volume, right? So rho into area into length is equal to volume into gravity. So now both should be equal, right? For attaining the terminal velocity. So I have equated both of them, and what I will get that after cancelling all these similar terms or the same terms, I get the value of velocity. Okay, and the velocity I'm getting is rho c d into g into d minus capital D minus small d divided by 8 into mu into velocity. Okay, so now they are changing the velocity, I mean the fluid's density and the viscosity. So now from the velocity expression we can say that velocity is independent of the density, right? There is no density term. I mean this is the density term of the solid cylinder. There is no density term of this fluid. Okay, so we can say that velocity is independent of the density rho, but it can change mu, right? I mean inversely proportional is given here, right? All other things are remains constant, but V is inversely proportional to the viscosity. So I've written here V is inversely proportional to viscosity. So I've written the final velocity divided by initial velocity, the initial viscosity divided by final viscosity, and I've equated that, and I got that V equal to 2 into V1. So option B is correct here. Okay. So I hope this lectures will be interesting to you, and I mean I've discussed quite few tough and interesting problem. So I mean in the next lecture I'm going to discuss some other problems as well. So till then keep learning and goodbye.